Alrighty, for our next example here, we're going to be comparing two processes for approximating numbers using tangent line linearization techniques. First, we're going to do a quick review here on example 12 about using linearization from section 2.9 to approximate the quartic root of 17. And for example 13, we're going to use Newton's method to approximate the quartic root. So let's first take a look at example 12 here and use the linearization technique to approximate quartic root of 17. First, recall that the linearization formula is given by L of x equals f of a plus f prime of a times x minus a. This is from section 2.9. Notice that this is just the equation for a tangent line, and what we're doing is we're going to use this linearization to plug in our x value of 17 in this case to calculate the y value to approximate the fourth root of 17. And we're going to complete this approximation by anchoring our tangent line at a friendly value, in which case we're going to use 16 because f of a is the fourth root of 16, which is 2. Our a value is a value at which our function is easy to calculate. I guess I should have said here as well that our function that we're going to be using to approximate is the fourth root of x, and we're going to plug our a value and our x value into this function. Before we do that though, we're going to need to calculate the first derivative, which is going to be easiest if we first simplify the original function using fractional powers. Now when we find the derivative, we get 1/4 x to the negative 3/4, which is just 1 over 4 times x to the third, the fourth root of that function. Now, let's build out our linearization. So in this case, L of x is going to equal f of 16 minus or plus f prime of 16 times x minus 16. And we're eventually going to plug 17 in for that x value, because that's where we want to evaluate this function to get the fourth root of 17. So alrighty here, so let's plug in 16 into each of our function and our derivative function. And if we do that, we can simplify. The fourth root of 16 is 2, and 16 to the 3/4 power is going to be 8, and we still have x minus 16 here. And now we can simplify that one step further. We get 2 plus 1 over 32 times x minus 16. And this is our linearization formula for the tangent line anchored at a equals 16. Now what we need to do is we need to approximate the fourth root of 17 by plugging in 17 into our linearization function, which means that we're going to plug in a 17 for the x value here in our linearization. Remember, our a is 16. And when we do that, we get 2 plus 1 over 32, which is... Alrighty, so let's take a look at what we're trying to accomplish here. So what we have is we have our function as the cube root of x, and the value that we're actually trying to calculate is the x value at 17 right here. And we're trying to find the y value, which is what happens when we plug 17 into the function. So the actual fourth root of 17 is 2.03054318487. Okay, now what we're going to do is we're going to take a point that's a little bit nicer. We're going to take the point at 16 because the y value of that point is 2, a nice clean number. And we're going to put a tangent line through that point at 16. Now we're going to need to zoom in a little bit to make this a little bit more obvious. So if we zoom in really closely here, we can see that our tangent line at 16 goes really close to this function. The function is actually close to a straight line as we zoom in here, but we see that they have a little gap right there at 17. So what we're going to do is we're going to evaluate the y value of this function right at 17, and our approximate value that we're going to find is going to be the y value of this approximation, which is 2.0313, and the y value of the actual function is 2.0305. So it's really close. It's 2 decimal places of accuracy, but it is off. We do see the error there, which is denoted by this slight vertical space. So again, linearization is using a tangent line to find an approximate y value. Now let's take a look at the work again. I'll give you a few seconds to pause to copy down some of this work. All right, now let's take a look at the next example. We're going to use Newton's method to do the exact same approximation, and we're going to see that we're going to get the same answer for x2. But what Newton's method allows us to do is do an iterative process where we can continually improve our answer, and we can actually calculate an x3 as a second iteration. Now first, let's recall that x sub n plus 1 is equal to x sub n minus f of x sub n divided by f prime of x sub n. This is in the Newton's method formula. We're going to be finding x values rather than y values like we did in the last problem. And our function, we want to choose a function so that the roots of the function are the exact value that we're trying to approximate. So again, we're going to do that by setting x equal to the value that we're trying to find. And then we're going to solve for this. We're going to solve this equation for 0 on one side. So we have x to the fourth equals 17. Subtract the 17, and we get x to the fourth minus 17 is equal to 0. This is going to be the function that we're going to use for Newton's method. Our x1 value is going to be our best guess at our answer. And for this problem, we want to choose that to be 2. And that's because the cube root, or the fourth root of 16 is equal to 2. And that should be close to the cube root of 17. We're also going to need the derivative of our original function. So f prime in this case is going to be 4x to the third. Now let's use all of this information to do our first approximation. So x2 is going to be equal to x1 minus f of x1 divided by f prime of x1, again the same Newton's method formula. So x2 in this case is going to be equal to 2 minus f of 2 divided by f prime of 2. Now let's go ahead and plug these in. So we get 2 minus 2 to the fourth minus 17 divided by 4 times 2 cubed, which is 2 minus 16 minus 17 divided by 2, 4 times 8, and then we get 2 minus negative 1 over 32, which ends up giving us 2 plus 1 over 32, which is exactly the answer that we got when we did our approximation using linearization, because both of these techniques are using tangent lines. Let's take a quick look at the graph of this first calculation to see what we're doing. So here's a look at our function f of x equals x to the fourth minus 7. And we can plug in our actual root on there, and we'll see that our actual root does go through the intersection of our function and the x-axis like we wanted. And we can put our first guess, our x sub 1 was at 2. We can see that those two numbers are not the same. But now if we put a tangent line through that point, we see that the tangent line, the root of that first tangent line, is getting really close already, even in just one iteration, to the actual root. And we can use our calculation of our first x2 value, and we get that x sub 2 is given by 2 plus 1 over 32, and that's right there on the x value, and that's a little bit bigger than our actual root, but we're getting closer and closer. Now, jumping back to our original problem, let's use Newton's method to do one step better and to do a second iteration to try to calculate x sub 3. So x sub 3 is equal to x sub 2 minus f of x sub 2 divided by f prime of x sub 2. And so we're going to get 2 plus 1 32nd minus f of 2 plus 1 32nd divided by f prime of 2 plus 1 32nd. This looks a little bit nasty, so let's go ahead and simplify this to be 63 32nds by getting some combination. Oops, made an error here. This should be 65 32nds, and that error should be carried through in the rest of the problem. Sorry about that. Denominators. So let's go change this to 63 32nds and each of these arguments to 63 32nds. So our substitution has been completed, and so we have 63 32nds minus 63 32nds to the fourth minus 17 divided by 4 times 63 32nds cubed. And again, this is going to be the final answer that you could type into your web work. But let's go ahead and take a look at the numerical approximation just so we can see what it looks like on the graph. If I plug these into a calculator really quickly, and so when we take a look at our numerical approximations here, for x2 we got 2.03125, and for x3 we got 2.0305435, and a bunch more decimals because it's a non-repeating decimal. And we can see that we're getting closer and closer to our exact value. That's all we're going to do for this problem. I'd just like to take a quick look at both of these examples. So in the linearization method, we used the linearization formula and we approximated using x values to find a y value that was our approximate fourth root of 17. For Newton's method, we used the Newton's method formula and a function that had the approximate value as its root, and then we used the iterative Newton's method formula to get our first approximation, which was equivalent to our approximation using linearization. But Newton's method allows us to find a second approximation that is more accurate than the first approximation. That's all we're going to do for this example. So I'll give you a couple of seconds to write down any of these notes, and then we'll move on to the next example in this video. All right, so let's take a look at the next example. This example is going to have us look at the graphical representation of Newton's method to get a little bit better sense about how Newton's method can go wrong, which was done in the second video that Ryan has posted. So we want to do Newton's method's approximations using different x1 values given this graph shown below. So if we choose x1 equals 0, what Newton's method is going to do is it's going to draw a tangent line through that point at 0, and then our second value here is going to be more negative, and then our third value is going to be even more negative, and our fourth value is going to be even more negative, and we're going to see that Newton's method in this case actually doesn't converge because it gets stuck in this horizontal asymptote. So that's one problem that can happen with Newton's method. For our second example, we're going to do our work in green, and we're going to see what happens when x1 is equal to 1. When we choose x1 to be 1, we get a horizontal tangent line, and Newton's method actually fails right there because we don't get an x2 where this first tangent line intersects with the x-axis. So it fails immediately because we have a horizontal tangent. In other words, f prime of x1 is equal to 0. Now what happens if x1 is equal to 5? If we take a look at that, if x1 is equal to 5, we have a nice tangent line right here, and our x2 value is just on the other side of this root at 6. So if we do our second tangent line right there, our second tangent line is going to get closer and closer to our actual root at x equals 6, and this is actually going to work, and it's going to approximate the root at x equals 6. So this works. Finds the root at x equals 6. So let's just take a look at those graphs again. So our first example where we chose x1 to be 0 didn't find this root at x equals 2 because we're on the other side of this critical point right here, which is going to cause the approximations to diverge as they follow this horizontal asymptote. If we chose our x1 to be 1, the Newton's method fails because we have a horizontal tangent line. And then if we choose our x1 to be 5, Newton's method works at approximating this root at x equals 6 because the function is nice over here to get us that approximation. All right, that's a little bit of a graphical explanation of Newton's method. Now let's finish this video off by doing these last examples, which are more similar to some of the problems that you'll see on WebWork. So again, recall that x2 is equal to x1 minus f of x1 divided by f prime of x1. This is the Newton's method formula, and this should clue us in that we need to find both our f of x function and we're given our x1 value. Remember, in this case, to find f of x, we need to find a function whose root is equal to the equation that we're trying to solve. So in this case, we're going to start by solving this equation for 0 on the right-hand side. And we're going to do that by simply subtracting our x squared. So cosine of x plus 1 minus x squared is equal to 0. So this cosine plus 1 minus x squared is the function that we're going to be working with. We're going to need the derivative, so let's calculate that right now. We get negative sine of x minus 2x. Now what we're going to do is we're going to plug in our x1 value into these functions to calculate x2. So x2 is equal to pi over 4 minus f of pi over 4 divided by f prime of pi over 4. And now if we simplify that, we get pi over 4 minus cosine of pi over 4 minus 1 plus 1 minus pi over 4 squared divided by the negative sine of pi over 4 minus 2 times pi over 4. It's kind of a mess there. Let's just simplify this one step and we're going to be done with this problem. So we have pi over 4 minus the cosine of pi over 4 is root 2 over 2 plus 1 minus pi squared over 16. If we square the top and square the bottom, we get a negative root 2 over 2 when we evaluate negative sine of pi over 4. And then we get a minus pi over 2 there if we simplify just a little bit. And then this is going to be the final answer that we type into WebWork because we cannot simplify this further without using a calculator. So that's more of an example of a medium level difficulty question where you're given an equation, you have to find your f of x by solving the equation for 0, and then you just need to plug in the x1 value that is given to you to find your x2 value. And we're not going to do any more with that problem. I'm going to give you a second to copy some of those notes. Now let's do the last example here, which is a pretty easy example after we get through this weird phrasing of the problem. We're trying to approximate a critical number. Now, the whole key here is, what is a critical number? Well, this is just where the first derivative is equal to 0. So, if we're trying to find a critical number of g of x, what we need to do is we need to calculate g prime of x. So I have my derivative here. G prime of x is equal to 4x to the 7th plus 4x to the 4th plus 2. And what I want to do is I want to find where g prime of x is equal to 0? Well, I can do that using Newton's method by just choosing my f of x and my Newton's method to be this derivative function 4x to the 7th plus 4x to the 4th plus 2. So this has nothing to do with any tricks having to do with Newton's method. It's just using Newton's method to find the 0 of a derivative. So all we're going to do, now that we've done this conversion from taking the derivative and setting the derivative equal to 0, now all we're going to do is we're going to use our new function, which is the derivative of the original function in this problem, and we're going to do Newton's method on this function with x1 equal to 1, which is given in the initial problem. So our f of x here is 4x to the 7th plus 4x to the 4th plus 2, and our f prime of x then is 28x to the 6th plus 16x cubed. And we're going to calculate x2 by doing x1 minus f of x1 divided by f prime of x1. So we're going to get that x2 is equal to 1 minus 4 times 1 to the 7th plus 4 times 1 to the 4th plus 2 divided by 28 times 1 to the 6th plus 16 times 1 to the 3rd. And if we simplify this, we get 1 minus 4 plus 4 plus 2 divided by 28 plus 16, or we get 1 minus 10 divided by 44, which is a number that is just a little bit less than 1, maybe something like 0.7. But all in all, this is going to be the answer that you plug in to your web work. All right, that's all the examples for today. Good luck on your web work, and don't hesitate to ask your instructors any questions during class if you're confused at all with any of this Newton's method stuff. See you next time.